Good evening, and welcome back to Boring Science for Sleep. Tonight, we're going to explore one of the most powerful and fascinating machines humanity has ever created, the rocket. Before we begin, settle in somewhere comfortable. Dim the lights if you can, relax your breathing, and let your mind slow down for a moment. And if you'd like, take a second to share something in the comments. Where in the world are you watching from tonight? And what time is it there right now? Many people enjoy listening to these space stories as they fall asleep, and it's always calming to see how listeners from all around the world are resting beneath the same night sky. Now, let's begin our quiet journey. Imagine standing far away from a launch pad in the early morning darkness. The air is still. The sky is deep blue just before sunrise, and in the distance stands a rocket, tall, silent, almost impossibly large. For hours it has waited there, filled with fuel and energy, ready for a journey that will carry it beyond Earth's atmosphere. Around it, technicians and engineers have prepared every system with extraordinary precision. Thousands of tiny details must be perfect, because launching a rocket is one of the most powerful events humanity can create. Then the countdown begins. 10, 9, 8. The rocket remains still, but inside it, fuel begins to flow. Valves open. Pumps accelerate. 7, 6. Deep beneath the rocket, engines prepare to ignite. 5, 4. Suddenly, the first flames appear. 3, 2. And then, everything changes. With a thunderous roar, engines ignite in a burst of fire and light. Columns of flame pour downward, brighter than the rising sun. The ground trembles as millions of newtons of thrust push against the launch pad. For a moment, the rocket seems to hesitate. Then, slowly, almost gently, it begins to rise. A machine weighing hundreds of tons lifts itself from the Earth. Fire and smoke roll across the ground. The rocket climbs higher and higher, leaving behind a glowing trail across the sky. Within minutes, it will travel faster than a bullet. Soon it will reach the edge of space. And eventually, it may circle the Earth, or travel toward the Moon, or even journey to other planets, all powered by the extraordinary physics of rocket engines. Tonight, we'll explore 100 fascinating facts about rocket launches. We'll discover how rockets work, why they are able to escape Earth's gravity, and how engineers carefully guide them through the atmosphere into orbit. Along the way, we'll visit some of the most famous launches in history, and we'll imagine the future rockets that may one day carry humans far beyond Earth. But for now, let the sound of distant engines fade into the quiet of space. Take a slow breath, and allow your thoughts to drift gently upward toward the stars. Long before rockets thundered into the sky, before astronauts floated in orbit, before satellites circled the Earth, the idea of traveling into space lived only in human imagination. For thousands of years, people looked up at the night sky and wondered what lay beyond. The moon drifted slowly across the darkness. Planets wandered among the stars, and the distant lights of the cosmos shimmered quietly above every civilization that had ever existed. But no matter how much people dreamed of reaching those distant worlds, there was one problem that seemed impossible to overcome: gravity. The Earth holds everything close to its surface. Every stone that is thrown eventually falls back down. Every bird that rises into the air must return to the ground. Even the tallest mountains barely reach the thin edges of the atmosphere. For most of human history, the idea of leaving the Earth entirely seemed as impossible as touching the stars themselves. Yet even in ancient times, people experimented with ways of creating thrust. One of the earliest ancestors of the modern rocket appeared in China more than 1,000 years ago. During the early development of gunpowder, inventors discovered that when certain mixtures of chemicals burned rapidly, they produced powerful jets of gas. At first, this discovery was used mainly for fireworks. Small tubes filled with gunpowder could shoot sparks into the sky, exploding in bright colors. But eventually someone realized that if the tube was left open on one end, the escaping gas would push the tube in the opposite direction. In other words, the tube would move. These early devices were simple and unpredictable, but they were the first true rockets. They were often attached to arrows and used in warfare. When ignited, they would launch themselves across the battlefield, trailing smoke and flame. Compared to modern rockets, they were crude and unreliable, but they demonstrated something important. A burning fuel could create thrust, and that thrust could move an object through the air. Centuries passed before anyone began to understand the deeper physics behind rockets. The key idea came from a simple principle of motion. Whenever something pushes in one direction, an equal force pushes back in the opposite direction. This principle would later be described formally by Isaac Newton as his famous third law of motion. But even before Newton wrote down the equation, people could observe this effect in everyday life. A balloon filled with air will shoot across a room when released. The escaping air pushes backward. The balloon moves forward. Rockets work in a similar way. Instead of air escaping from a balloon, extremely hot gases shoot out of a rocket engine. Those gases rush downward at tremendous speed, and the rocket is pushed upward. Still, for centuries, rockets remained mostly small devices used for fireworks and simple weapons. No one seriously imagined using them to travel beyond the Earth. The idea seemed far too unrealistic, until one quiet schoolteacher in Russia began thinking about it. His name was Konstantin Tsiolkovsky, and he would become one of the most important pioneers in the history of spaceflight. Tsiolkovsky lived in the late 19th and early 20th centuries. He spent much of his life working as a mathematics teacher in a small town, but in his spare time, he thought deeply about the possibility of space travel. Unlike many people of his era, Tsiolkovsky believed that reaching space might actually be possible. He understood that rockets did not need air in order to work. This was a crucial insight. Many people once believed that rockets could not function in the vacuum of space because there would be nothing for the rocket to push against. But Tsiolkovsky realized that rockets push against their own exhaust gases. As long as fuel burns and gases shoot out of the engine, the rocket will continue to accelerate, even in the vacuum of space. In 1903, Tsiolkovsky published a remarkable scientific paper describing the mathematics of rocket propulsion. In this paper, he introduced what is now known as the rocket equation. This equation explains how a rocket's speed depends on the velocity of its exhaust and the ratio between its fuel mass and its empty mass. Although the equation may appear complicated, its meaning is simple. To reach high speeds, rockets must carry large amounts of fuel. But carrying fuel also adds weight, and the heavier the rocket becomes, the harder it is to accelerate. Tsiolkovsky realized that solving this problem would require rockets built in multiple stages. The idea of multi-stage rockets was revolutionary. Instead of a single rocket carrying all its fuel from start to finish, a rocket could be built in sections. Once the fuel in one stage was used up, that stage could be discarded. The remaining rocket would then be lighter and able to accelerate more efficiently. This concept would later become essential for launching spacecraft into orbit. Nearly every modern rocket still follows this basic principle. Tsiolkovsky also imagined technologies that would not become reality until many decades later. He wrote about space stations orbiting the Earth, about spacecraft traveling between planets, and even about human colonies living in space. At the time, these ideas sounded like science fiction. After all, no rocket had ever reached space. No human had ever left the Earth. Yet Tsiolkovsky believed that humanity's future lay beyond our planet. One of his most famous lines captured that vision perfectly. "The Earth is the cradle of humanity, but mankind cannot stay in the cradle forever." Although Tsiolkovsky himself never built a rocket, his ideas inspired generations of engineers and scientists. His equations provided the foundation for modern rocket science. Later pioneers such as Robert Goddard in the United States and Hermann Oberth in Europe would begin turning those theories into real machines. Slowly, the dream of leaving Earth began moving from imagination to engineering. From sketches and equations to engines and fuel tanks. From quiet thoughts written on paper to roaring rockets rising into the sky. And so the dream that once seemed impossible began to take shape. Humans had always looked up at the stars with wonder. Now, for the first time, they were beginning to understand how a machine might carry them there. The journey to space had not yet begun, but the idea of it, the dream of leaving Earth, had already taken flight. And in the next part of our journey, we will explore the physics that makes rockets possible. Because the secret behind every rocket launch lies in a simple but powerful law of motion. A law that explains how fire and fuel can lift hundreds of tons into the sky and send them racing towards space. Now that we have explored the early dream of leaving Earth, we arrive at one of the most fascinating questions in all of spaceflight. How does a rocket actually work? At first glance, rockets seem almost magical. A massive machine, often weighing hundreds of tons, rises slowly into the sky, surrounded by roaring flames and clouds of smoke. Within minutes, it accelerates faster than the speed of sound, eventually traveling fast enough to remain in orbit around the Earth. But behind this dramatic spectacle lies a simple physical principle. A principle that was first described more than 300 years ago by Isaac Newton. Newton's third law of motion. This law states something very straightforward. For every action, there is an equal and opposite reaction. It may sound abstract at first, but this rule appears everywhere in everyday life. If you push against a wall, the wall pushes back against you. If you jump off a small boat into the water, the boat moves backward. And if air rushes out of a balloon, the balloon shoots forward in the opposite direction. Rockets operate according to exactly the same principle. Inside a rocket engine, fuel and oxidizer are mixed together and burned in an extremely powerful chemical reaction. This reaction produces enormous amounts of hot gas. The gas expands rapidly as it heats up, creating pressure inside the engine's combustion chamber. But the gas cannot escape in every direction. Instead, it is forced through a narrow opening at the bottom of the engine called the nozzle. As the gas rushes out of the nozzle at tremendous speed, it shoots downward. And according to Newton's third law, if the exhaust gas is pushed downward, the rocket itself must be pushed upward. This upward push is known as thrust. Thrust is the force that lifts the rocket from the launch pad and drives it towards space. The amount of thrust produced by a rocket depends on two main factors. First, how much mass is expelled from the engine. Second, how fast that mass is expelled. The more gas that flows through the engine and the faster it leaves the nozzle, the greater the thrust. Rocket engines therefore operate under extreme conditions. Inside the combustion chamber, temperatures can reach thousands of degrees. The pressure becomes immense. Fuel is burned at astonishing rates, sometimes hundreds of kilograms every second. All of this energy is converted into a powerful stream of exhaust gas shooting out of the rocket. And that stream of gas is what lifts the rocket skyward. One of the most interesting features of rockets is that they carry both fuel and oxidizer. This might seem unusual at first. Most engines on Earth, such as car engines or jet engines, burn fuel using oxygen from the surrounding air. But rockets cannot rely on the atmosphere. Once a rocket reaches space, there is no air available. Without oxygen, ordinary combustion would stop. So rockets bring their own oxygen with them in the form of an oxidizer. Inside the rocket's tanks, the fuel and oxidizer are stored separately. They are pumped into the engine where they mix and ignite. This allows rockets to function not only within the atmosphere but also in the vacuum of space. It is one of the key differences between rockets and other types of engines. Many different types of rocket fuel have been used throughout the history of spaceflight. Some rockets use liquid fuels, which are stored in tanks and pumped into the engine. For example, one common combination is liquid hydrogen as fuel and liquid oxygen as oxidizer. This mixture burns extremely efficiently and produces very high exhaust speeds. The exhaust from hydrogen engines is mostly water vapor. Other rockets use kerosene-based fuels, similar to refined rocket-grade kerosene known as RP1. When combined with liquid oxygen, kerosene produces powerful thrust and is easier to store than hydrogen. This type of fuel has been used in many famous rockets, including the Saturn V that carried astronauts to the moon. There are also rockets that use solid fuel. Instead of liquids stored in tanks, solid rocket motors contain a mixture of fuel and oxidizer packed into a solid block. When ignited, the fuel burns steadily until it is completely consumed. Solid rockets are simpler than liquid engines because they have fewer moving parts. However, once they are ignited, they cannot easily be turned off. For this reason, solid rocket boosters are often used during the early stages of launch when maximum thrust is needed. The Space Shuttle, for example, used 2 enormous solid rocket boosters to help lift the spacecraft from the launch pad. Another important part of rocket design is the shape of the engine's nozzle. The nozzle is carefully engineered to accelerate exhaust gases to extremely high speeds. Inside the combustion chamber, gases begin under very high pressure. As they flow through the narrow throat of the nozzle and expand outward, their speed increases dramatically. By the time the gases exit the nozzle, they may be traveling several kilometers per second. This incredible speed is what gives rockets the ability to produce such powerful thrust. Despite their enormous power, rockets must overcome one major challenge. They are extremely heavy at liftoff. Most of a rocket's weight is not the spacecraft itself. It is the fuel. In fact, in many rockets, more than 90% of the total mass at launch is fuel and oxidizer. As the rocket burns fuel during ascent, it gradually becomes lighter. This allows it to accelerate more easily. The physics of this process was first described by Tsiolkovsky's rocket equation, which we discussed earlier. The equation shows that achieving high speeds requires burning large amounts of propellant. That is why rockets are often so large and carry enormous fuel tanks. When you watch a rocket launch, the flames and smoke may appear chaotic, but in reality, the process is incredibly precise. Thousands of sensors monitor temperature, pressure, fuel flow, and engine performance. Computers constantly adjust the engine's operation to maintain stable thrust. Guidance systems ensure the rocket follows its planned trajectory. Every second of the launch must be carefully controlled, because even a small error could lead to failure. Yet when everything works perfectly, the result is extraordinary. A machine built on Earth rises through the sky, powered only by fire, fuel, and the simple physics of Newton's laws. And as the rocket climbs higher and higher, another phase of the journey begins. Because reaching space is not only about producing thrust, it is also about surviving the intense forces that occur during ascent through the atmosphere. The air becomes thinner, the rocket accelerates faster, and the stresses on the vehicle grow stronger. In the next part of our journey, we will explore the carefully orchestrated process that leads up to every launch, the quiet preparations, the final checks, and the dramatic countdown that begins just moments before the engines ignite. Long before a rocket rises into the sky, the most delicate part of the journey has already begun. The countdown. To an outside observer, a rocket launch might appear to happen suddenly. One moment, the rocket stands quietly on the launch pad. The next moment, flames burst from its engines and it climbs into the sky. But in reality, a launch is the result of many hours, sometimes even days, of careful preparation. Every system must be checked. Every sensor must be monitored. Every valve and computer must operate perfectly. Because once the engines ignite, there is very little time to correct mistakes. The process begins many hours before liftoff. Engineers and technicians gather in control rooms filled with screens and instruments. Some sit inside the launch control center near the rocket itself. Others work from mission control facilities hundreds or even thousands of kilometers away. Together, they monitor thousands of parameters: fuel levels, temperatures, pressure inside the tanks, electrical systems, communication links, navigation systems. Each of these elements must be working properly before the launch can continue. Meanwhile, the rocket itself remains standing quietly on the launch pad. At this stage, it is often connected to large structures known as launch towers. These towers provide access to the rocket for technicians and supply systems for fuel, power, and data. From a distance, the rocket may appear still and silent, but inside it, preparations are already underway. Valves are tested, pumps are checked, sensors measure the conditions within the vehicle. The rocket is slowly coming to life. One of the most important steps during the countdown is fueling. Rocket propellants are often extremely cold liquids. For example, liquid hydrogen must be stored at temperatures near -250 degrees Celsius. Liquid oxygen is also cryogenic, meaning it must remain extremely cold to stay in liquid form. Fueling a rocket with these propellants requires careful timing. The tanks are gradually filled while engineers monitor temperature and pressure. Pipes and valves must remain stable despite the extreme cold. Even small leaks or temperature changes can cause serious problems. For this reason, fueling operations are among the most critical phases of the countdown. As the launch window approaches, the pace of activity begins to increase. More systems come online. Computers begin running automated checks. Engineers carefully review the data flowing across their screens. If anything appears unusual, the countdown can be paused. This is known as a hold. During a hold, the clock stops while teams investigate the issue. Sometimes the problem can be solved quickly. Other times the launch must be postponed to another day. Safety always comes first. Inside mission control, the atmosphere is often surprisingly calm. Despite the complexity of the operation, the room remains quiet. Controllers speak clearly and precisely over communication loops. Each specialist is responsible for a specific system. One person monitors propulsion, another watches electrical systems, another tracks navigation and guidance. One by one, they report their status. Propulsion is go, guidance is go, flight computers are go. These confirmations gradually build toward the final decision, whether the rocket is ready to fly. As the countdown reaches its final minutes, more processes become automated. The rocket's onboard computers begin controlling many of the systems directly. Fuel tanks are pressurized. Engine chill-down procedures begin, allowing extremely cold propellants to flow through the engines before ignition. This prepares the hardware for the sudden rush of fuel that will soon follow. At this stage, even small details are carefully managed. Wind conditions are measured. Weather radar scans the sky for lightning or storms. Range safety officers ensure the launch corridor is clear. Every factor must align before the rocket can leave the ground. Then the final countdown begins. 10 minutes, 5 minutes, 1 minute. Inside mission control, voices remain steady as each milestone passes. 30 seconds. At this moment, the rocket is almost entirely in control of itself. Its computers monitor every system. If something goes wrong, the rocket can automatically abort the launch. But if everything remains within safe limits, the sequence continues. 10 seconds. The rocket's engines prepare to ignite. Valves open. Fuel begins rushing into the combustion chambers. 9, 8. The engines begin their startup sequence. 7, 6. Inside the rocket, turbopumps spin faster and faster, forcing fuel and oxidizer toward the engines. 5, 4. Flames begin to appear beneath the rocket. 3, 2. The engines reach full power. And finally, 1. At that moment, the enormous clamps holding the rocket to the launch pad release. For a brief instant, the rocket seems to hover. Then, slowly, almost gently, it begins to rise. Flames spread across the launch pad. Clouds of steam and smoke roll outward. The rocket climbs into the sky, carrying its cargo towards space. The countdown is over. The journey has begun. But the rocket's challenge is only just beginning. Within seconds, it will accelerate to incredible speeds. The atmosphere will push against it with enormous force, and the vehicle must remain stable as it climbs toward orbit. In the next part of our journey, we will explore the moment of liftoff itself, the thunderous power of rocket engines, and the immense energy required to lift a spacecraft away from the Earth. For hours, the rocket has stood quietly on the launch pad, fuel tanks filled, systems checked, computers ready. Then, in a matter of seconds, everything changes. The engines ignite. A burst of light appears beneath the rocket, growing brighter and brighter as the fuel begins to burn. Flames spread outward across the launch platform, glowing orange and white against the early morning sky. The quiet stillness of the launch pad is replaced by one of the most powerful forces humans have ever created. The moment of liftoff has arrived. Rocket engines produce extraordinary amounts of energy. Inside each engine, fuel and oxidizer mix together and burn at temperatures hotter than molten lava. The resulting gases expand rapidly, rushing through the engine's nozzle and blasting downward at incredible speed. The force created by this exhaust is enormous. For example, the Saturn V rocket, which carried astronauts to the moon, produced about 35 million newtons of thrust at liftoff. That is roughly equivalent to the combined power of dozens of large jet aircraft engines operating at once. It is the kind of energy required to lift a machine weighing thousands of tons into the sky. But before the rocket begins to move, something interesting happens. The engines ignite first, while the rocket remains firmly held in place by large clamps on the launch pad. For a few seconds, the engines run at full power. Sensors measure the thrust and check that each engine is operating correctly. Only when everything is confirmed to be functioning properly do the clamps release. This short moment ensures that the rocket will not attempt to launch if any engine is underperforming. Once the clamps release, gravity and thrust compete. At first, the rocket rises slowly. This surprises many people who expect rockets to leap instantly into the sky. But the rocket's thrust is only slightly greater than its weight at liftoff, so the vehicle climbs gently at first, almost as if it is carefully lifting itself away from the Earth. Beneath the rocket, the flames are astonishing. The exhaust plume can reach temperatures of several thousand degrees. The gases move so quickly that they form powerful shock waves as they collide with the ground and surrounding air. Large clouds of steam often billow across the launch pad. This steam is sometimes created intentionally by water systems that flood the launch platform just before ignition. The water helps cool the surface and reduce the intense acoustic energy produced by the engines. Without this system, the sound waves could potentially damage the rocket itself. The sound of a rocket launch is unlike anything most people have ever heard. At a safe viewing distance, spectators often see the rocket begin rising silently. Then, several seconds later, the sound finally arrives. A deep, rolling thunder that seems to shake the ground. The noise can exceed 180 decibels near the launch pad, louder than almost any other human-made sound. It is not just a single roar. Instead, it is a complex mixture of vibrations, shock waves, and rumbling energy. The air itself seems to tremble. Even buildings several kilometers away may feel the vibration. Inside the rocket, astronauts, if there are any aboard, experience the launch in a very different way. Instead of hearing the external roar clearly, they feel powerful vibrations through the spacecraft. The engines generate enormous mechanical forces that travel through the structure of the rocket. Seats and harnesses hold the astronauts firmly in place. As the rocket climbs, they feel the pressure of acceleration pushing them into their seats. At liftoff, the force may be only slightly greater than normal gravity. But as the rocket burns fuel and becomes lighter, the acceleration gradually increases. Soon, the astronauts may experience 2, 3, or even 4 times the force of gravity. Despite the intense forces, the ride is carefully controlled. Modern rockets are designed to minimize dangerous vibrations that could damage the spacecraft or injure the crew. Engineers study the physics of these vibrations in great detail to ensure a safe ascent. Another fascinating aspect of liftoff is the enormous amount of fuel consumed during the first minutes of flight. Rocket engines burn propellant at astonishing rates. For example, the Saturn V consumed roughly 13 tons of fuel every second during its first stage burn. Imagine an entire truckload of fuel disappearing every second. Yet this massive consumption is necessary. Escaping Earth's gravity requires enormous energy, and that energy must come from the chemical reactions occurring inside the rocket's engines. As the rocket rises higher, it begins to accelerate more quickly. The engines continue firing at full power. The vehicle climbs through the lower atmosphere, leaving behind a long trail of exhaust. From the ground, this trail often appears as a brilliant white plume stretching across the sky. Sunlight reflecting from the exhaust can make the rocket visible from hundreds of kilometers away. For observers on the ground, the sight can be breathtaking. A glowing pillar of fire carrying a spacecraft toward the edge of space. Yet even during this dramatic ascent, the rocket must follow a carefully planned trajectory. It does not travel straight upward for very long. Instead, it gradually begins to tilt sideways. This maneuver is called the gravity turn. The goal is not simply to rise high above the Earth. The goal is to build horizontal speed. Because reaching orbit requires moving sideways around the planet at incredible velocity. The rocket must therefore begin turning toward its orbital path soon after liftoff. Within just a few minutes, the rocket will already be traveling faster than the speed of sound. Soon after that, it will approach several kilometers per second. The violent energy of liftoff gradually gives way to the smooth acceleration of high-altitude flight. But during those first moments on the launch pad, when engines ignite and flames erupt beneath the rocket, humanity witnesses one of its most dramatic technological achievements. A machine powerful enough to rise from the Earth, carried upward by fire, fuel, and physics. And as the rocket climbs higher through the sky, it faces its next great challenge. The atmosphere itself. Air rushing past the rocket creates enormous aerodynamic forces. At a certain point during ascent, those forces will reach their maximum, a moment known as max Q. In the next part of our journey, we will explore how rockets break through the atmosphere and survive the intense pressure of their climb towards space. After the thunderous moment of liftoff, the rocket continues its journey upward through the sky. Below it, the launch pad quickly disappears beneath clouds of smoke and steam. The vehicle accelerates rapidly, climbing higher and higher as its engines burn through massive quantities of fuel. But even though the rocket is heading toward the vacuum of space, its first challenge is not empty space. It is the atmosphere. The Earth's atmosphere forms a vast ocean of air surrounding the planet. From the ground up to the edge of space, the rocket must travel through layers of gas that push against it as it accelerates. At first, the air is thick and heavy, but as the rocket climbs, the atmosphere gradually becomes thinner. The rocket must be carefully designed to survive this transition. The lowest layer of the atmosphere is called the troposphere. This is the region where weather occurs. Clouds form here. Storms develop. Airplanes fly within this layer. The troposphere extends roughly 10 to 15 kilometers above the Earth's surface. When a rocket launches, it passes through this region within the first minute or two of flight. During this phase, the rocket experiences strong aerodynamic forces. Air rushes past the vehicle at increasing speed. The faster the rocket moves, the harder the air pushes against it. This resistance is known as aerodynamic drag. As the rocket accelerates, something interesting happens. Even though the atmosphere becomes thinner as altitude increases, the rocket's speed is increasing at the same time. For a short period during ascent, these two effects combine in a very important way. The rocket is moving extremely fast while still passing through relatively dense air. This creates the moment of greatest aerodynamic stress during the entire launch. This moment is known as max Q. The name comes from the letter Q, which engineers use to represent dynamic pressure, the force created by air pushing against a moving object. At max Q, the pressure on the rocket's structure reaches its maximum value. During this critical moment, the rocket experiences enormous forces. The air rushing past the vehicle presses against its surface. The rocket's body bends slightly under the stress. The engines continue pushing upward while aerodynamic forces push against the sides of the vehicle. Engineers must carefully design rockets to withstand these stresses without breaking apart. Even small structural weaknesses could become dangerous during max Q. For this reason, rocket designers spend years studying how aerodynamic forces affect every part of the vehicle. Interestingly, rocket engines are sometimes throttled down during max Q. This means the engines temporarily reduce their power. By slightly lowering the thrust, the rocket's acceleration decreases for a short time. This prevents the aerodynamic pressure from becoming too extreme. Once the rocket climbs higher and the air becomes thinner, the engines can safely return to full power. Many astronauts describe this moment during launch. They feel the engines briefly reduce thrust, then surge again as the rocket passes through max Q. It is one of the many, carefully controlled phases of ascent. The shape of the rocket itself also plays a crucial role in surviving atmospheric flight. Rocket bodies are designed to be aerodynamic. This means they are shaped in a way that reduces drag and allows air to flow smoothly around the vehicle. The long cylindrical body and pointed nose cone help minimize resistance as the rocket slices through the atmosphere. Without this streamlined shape, the rocket would experience far greater drag and heating during ascent. The design of the nose cone is especially important. As the rocket moves faster and faster, air compresses in front of the vehicle. This can create intense heating. The smooth, tapered shape helps reduce this effect. Attached to the top of many rockets is a structure known as the payload fairing. The fairing protects the spacecraft or satellite during the early stages of flight. Inside it, delicate equipment must remain safe from aerodynamic forces and heating. The fairing acts like a protective shell, shielding the payload while the rocket passes through the thickest parts of the atmosphere. But once the rocket climbs high enough, the atmosphere becomes extremely thin. At that point, the fairing is no longer needed. Carrying unnecessary weight would only slow the rocket down. So the fairing separates from the vehicle and falls away. From the ground, this event is rarely visible. But high above the Earth, the rocket becomes lighter and more efficient as it continues towards space. By this stage of the flight, the rocket is already traveling incredibly fast. Within just a few minutes after liftoff, It may be moving several times the speed of sound. The air around it becomes thinner and thinner. Eventually, the rocket reaches the upper layers of the atmosphere. Here, the sky grows darker. The blue of the daytime sky fades into deep black. Stars begin to appear even while the sun shines brightly below. This transition marks the rocket's gradual arrival at the edge of space. Above the troposphere lies the stratosphere, where the ozone layer absorbs much of the sun's ultraviolet radiation. Higher still are the mesosphere and thermosphere, where the atmosphere becomes so thin that individual molecules are separated by vast distances. By the time the rocket reaches these heights, aerodynamic forces are greatly reduced. The vehicle is now moving through air that is barely there at all. The roaring struggle against the atmosphere slowly fades. The rocket's journey becomes smoother and quieter. But the climb is not finished yet. Even though the rocket has nearly escaped the atmosphere, it still needs one more essential element to complete its journey: speed. To remain in orbit around the Earth, the spacecraft must travel sideways at incredible velocity. Reaching this speed requires another clever feature of rocket design: the use of multiple stages. In the next part of our journey, we will explore how rockets shed empty fuel tanks and continue accelerating higher into space, a process that allows them to overcome gravity and carry their payloads into orbit around our planet. As the rocket climbs higher into the sky, something remarkable begins to happen. Parts of the rocket start to fall away. To someone watching from the ground, this may sound alarming, but in the world of rocket engineering, it is not a failure at all. It is a carefully planned event. One of the most important ideas that makes modern spaceflight possible: the concept of multi-stage rockets. Earlier, we learned that rockets must carry enormous amounts of fuel. In fact, most of the mass of a rocket at liftoff is not the spacecraft itself. It is the propellant needed to escape Earth's gravity. But this creates a difficult problem. Once the fuel in a tank has been burned, the empty tank becomes useless weight. If the rocket continues carrying that empty structure, it must spend extra energy accelerating something that no longer serves a purpose. Engineers therefore came up with a clever solution. Instead of building one single rocket, they build several rockets stacked on top of each other. Each section is called a stage. A multi-stage rocket works like a relay race. The first stage does the hardest work. It lifts the entire vehicle from the launch pad and pushes it through the thick lower atmosphere. This stage carries powerful engines and large fuel tanks. But once its fuel is exhausted, the first stage has done its job. Instead of continuing to carry the empty tanks, the rocket releases that stage. Large mechanical clamps separate the structure. Small explosive bolts or pneumatic systems trigger the release, and the empty stage falls away from the rest of the rocket. Suddenly, the vehicle becomes lighter. The remaining stages can now accelerate more efficiently. The moment of stage separation is one of the most dramatic parts of a launch. High above the Earth, the empty booster detaches and drifts away. Sometimes small separation motors push the stage slightly backward to ensure a safe distance. Meanwhile, the engines of the next stage ignite. For a brief moment, there is a pause between the shutdown of one stage and the ignition of the next. Then the new engines burst to life, continuing the climb towards space. The rocket moves faster and faster as each stage contributes its portion of energy. The importance of staging was first described mathematically by Konstantin Tsiolkovsky. His rocket equation revealed that achieving high speeds requires extremely high fuel mass. But if a rocket carries all its empty tanks for the entire flight, it becomes inefficient. By discarding those empty sections along the way, the rocket effectively sheds weight. This makes it easier to accelerate the remaining mass. The result is a far more efficient vehicle. Without staging, reaching orbit would be vastly more difficult. In many cases, it might even be impossible with chemical rockets. Most rockets today use 2 or 3 stages. The first stage provides the enormous thrust needed to escape the launch pad and climb through the lower atmosphere. The second stage continues accelerating the rocket once it reaches higher altitudes where the air is thinner. In some missions, a third stage may ignite later to push the spacecraft even faster. This final stage might send a satellite into high orbit or propel a spacecraft toward the Moon or other planets. Each stage is optimized for its specific task. The engines used in different stages may also vary. First stage engines must produce enormous thrust to lift the rocket against gravity. They often burn fuel very quickly and generate massive exhaust plumes. Upper stage engines, on the other hand, operate in the vacuum of space. In this environment, engines can use larger nozzles designed to expand exhaust gases more efficiently. These engines may produce less thrust than first-stage engines, but they are optimized for efficiency and long-duration burns. Together, the stages work in harmony, gradually increasing the rocket's speed. For many decades, the stages of rockets simply fell back to Earth after separation. The first stage would drop into the ocean or burn up in the atmosphere. This was considered normal. Rocket launches were expensive, and most of the hardware was used only once. But in recent years, a new development has changed the way some rockets operate. Some boosters are now designed to return to Earth and land safely after separation. Companies like SpaceX have developed rockets whose first stages perform controlled descents and land vertically on landing pads or floating platforms at sea. Watching a massive rocket booster descend slowly and land upright has become one of the most extraordinary sights in modern spaceflight. It represents a major step toward reusable rockets. Even with reusable boosters, the principle of staging remains essential. Each stage plays a specific role in overcoming gravity and building speed. Without staging, rockets would need to carry enormous amounts of extra fuel. The vehicle would become too heavy to launch efficiently. By dividing the journey into stages, engineers allow each part of the rocket to contribute its energy at the right moment. Once that task is complete, the empty hardware can be discarded. The rocket becomes lighter, faster, more efficient. By the time the final stage ignites, the rocket may already be hundreds of kilometers above the Earth. The atmosphere has nearly vanished. The sky is completely black. Below, the curvature of the planet becomes visible. At this point, the rocket is no longer simply climbing upward. Its mission has changed. It must now achieve a very specific speed, a speed that allows it to remain in orbit around the Earth. And reaching that speed requires one final step in our journey through rocket science: understanding how spacecraft achieve the incredible velocities needed to circle the planet without falling back to the ground. By the time a rocket has burned through its early stages and climbed beyond most of the atmosphere, it has already traveled hundreds of kilometers above the Earth. From this altitude, the planet begins to look very different. The sky is no longer blue. Instead, it fades into deep black. The thin glow of the atmosphere forms a faint blue curve along the edge of the Earth. Clouds drift slowly across the continents far below, and above the rocket, the stars shine clearly even in daylight. At this point, the rocket is approaching the edge of space. But surprisingly, reaching space is not the main challenge. The real challenge is staying there. Many people imagine that spacecraft reach orbit simply by flying upward high enough, but this is not quite how it works. In fact, altitude alone is not enough to remain in space. Even if a rocket were able to fly straight up to a height of several hundred kilometers, gravity would still be pulling it back toward Earth. Without sufficient speed, the spacecraft would eventually fall back down. To remain in orbit, a spacecraft must achieve an incredible sideways velocity. Instead of simply climbing upward, it must travel fast enough to continuously fall around the Earth without ever hitting the ground. This delicate balance between speed and gravity is what creates orbit. For spacecraft circling the Earth in low Earth orbit, this required speed is roughly 28,000 kilometers per hour. That is about 7.8 kilometers per second. At this velocity, the spacecraft moves so quickly that as it falls toward the Earth under gravity, the surface of the planet curves away beneath it. The result is a continuous state of falling that never ends. The spacecraft keeps missing the Earth as it moves forward, and so it circles the planet again and again. This is what we call orbit. The idea can be imagined with a simple thought experiment. Suppose you stood on a very tall mountain and threw a ball forward. At first, the ball would travel a short distance before falling to the ground. If you threw it faster, it would travel farther before landing. Now imagine throwing it faster and faster. Eventually, if the ball moved fast enough, the Earth would curve away beneath it at the same rate that gravity pulled it downward. The ball would never touch the ground. Instead, it would continue circling the planet. This is essentially how orbit works. Only rockets must accelerate spacecraft to extremely high speeds to achieve it. Because orbit depends on sideways velocity, rockets do not travel straight upward for very long. Shortly after liftoff, the rocket begins a maneuver known as the gravity turn. Instead of pointing straight up, the rocket slowly tilts sideways. At first, the angle is very small, but as the rocket climbs higher, the tilt becomes more pronounced. This maneuver allows the rocket to gradually build horizontal speed while still gaining altitude. By the time the rocket reaches space, much of its motion is already directed sideways. This is exactly what is needed for orbit. The final stage of the rocket is responsible for reaching the precise velocity required. Its engines ignite in the near vacuum of space, where there is almost no atmospheric drag. During this burn, the spacecraft accelerates rapidly. Guidance computers carefully adjust the engine's thrust and direction. Every second of this burn is calculated with extraordinary precision. Too little speed, and the spacecraft will fall back into the atmosphere. Too much speed, and it may escape Earth's gravity entirely. Achieving the correct velocity is like threading a needle on a cosmic scale. Once the engines shut down, the rocket stage may release the spacecraft. Suddenly, the violent acceleration of launch disappears. Inside the spacecraft, astronauts or instruments experience weightlessness. They float freely inside the cabin. But this weightlessness does not occur because gravity has vanished. Gravity is still very strong, even hundreds of kilometers above the Earth. Instead, the spacecraft and everything inside it are falling together around the planet. Since everything is falling at the same rate, there is no sensation of weight. From orbit, the Earth moves slowly beneath the spacecraft. A full trip around the planet can take roughly 90 minutes for objects in low Earth orbit. Astronauts aboard the International Space Station see the sun rise and set many times during a single day. Cities glow softly at night. Lightning storms flash within swirling clouds. The thin blue atmosphere appears fragile and delicate from this vantage point. Orbit reveals how small and beautiful our planet truly is. But reaching orbit is only the beginning of many journeys. Some spacecraft remain circling the Earth. Others ignite their engines again to travel farther outward. Satellites may climb to higher orbits thousands of kilometers above the planet. Spacecraft heading to the Moon or Mars accelerate beyond Earth's gravitational hold entirely. Each mission begins with the same fundamental challenge: achieving the speed necessary to leave the surface of the Earth. From the outside, a rocket launch may appear to be a simple vertical ascent. But the true goal of the rocket is something more subtle. Not just height, but speed. Speed great enough to circle the planet. Speed great enough to escape gravity. Speed great enough to carry human exploration deeper into the solar system. And once that speed is achieved, the door to the rest of the cosmos begins to open. In the next part of our journey, we will explore some of the most famous rocket launches in history. moments when humanity first crossed new frontiers on its path toward the stars. Throughout the history of space exploration, certain rocket launches have stood out as turning points, moments when humanity pushed beyond previous limits, moments when technology, courage, and imagination came together to send machines and sometimes people far beyond the surface of the Earth. Among the many rockets that have lifted humanity toward space, a few have become especially famous. Their launches are remembered not only for their engineering brilliance, but also for the way they changed our understanding of what is possible. Tonight, we will quietly visit three of the most remarkable rockets ever built: the Saturn V, the Space Shuttle, and the Falcon 9. Each represents a different era in the story of spaceflight. The story of the Saturn V begins during one of the most ambitious periods in human history. In the 1960s, the United States and the Soviet Union were competing in what became known as the space race. Both nations were determined to demonstrate their technological capabilities by exploring space. In 1961, US President John F. Kennedy announced a bold goal. Human beings would land on the moon before the end of the decade. To achieve that goal, engineers needed a rocket far more powerful than anything that had ever been built before. The result was the Saturn V. The Saturn V remains one of the largest and most powerful rockets ever constructed. Standing about 110 meters tall, it was taller than many skyscrapers. Fully fueled, it weighed nearly 3,000 tons. Yet this enormous machine was designed to do something extraordinary: carry astronauts all the way to the moon. At liftoff, the Saturn V's first stage ignited 5 massive F1 engines. These engines burned refined kerosene and liquid oxygen, producing an immense column of fire beneath the rocket. Together, they generated about 35 million newtons of thrust. The sound of a Saturn V launch could be heard many kilometers away. The ground itself seemed to tremble as the rocket rose slowly into the sky. The Saturn V flew a total of 13 times, and every launch was successful. Among these missions were the famous Apollo moon landings. In July 1969, a Saturn V carried the Apollo 11 spacecraft into orbit. Inside the spacecraft were astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins. Several days later, Armstrong and Aldrin became the first humans to walk on the moon. The rocket that carried them there had lifted them from Earth with the power of millions of kilograms of burning fuel. Even today, watching footage of a Saturn V launch can feel awe-inspiring. It remains a symbol of one of humanity's greatest achievements. After the Apollo era ended, space exploration began to evolve in a new direction. Instead of building a new rocket for every mission, engineers began thinking about reusable spacecraft. The idea was simple but ambitious. If parts of the launch system could return safely to Earth and fly again, space travel might become more affordable and frequent. This vision led to the creation of the Space Shuttle. The Space Shuttle was unlike any rocket that had come before. Rather than a single rocket carrying a capsule, the shuttle consisted of several parts working together. At the center was the orbiter, a winged spacecraft that looked somewhat like an aeroplane. Attached to the orbiter were 2 large solid rocket boosters, and beneath it all sat a massive orange external fuel tank. During launch, the shuttle's main engines and the 2 boosters ignited together. The result was a spectacular column of flame and smoke as the shuttle climbed into the sky. The shuttle's solid rocket boosters were extremely powerful. They provided most of the thrust during the first 2 minutes of flight. Once their fuel was exhausted, the boosters separated from the shuttle and parachuted back into the ocean, where they were recovered and refurbished for future missions. Meanwhile, the shuttle's main engines continued firing, drawing fuel from the external tank. After reaching orbit, the empty tank detached and burned up in the atmosphere. Only the orbiter remained in space. The most remarkable feature of the Space Shuttle was its ability to return to Earth and land like an aircraft. After completing its mission in orbit, the shuttle would re-enter the atmosphere and glide toward a runway. Its heat-resistant tiles protected the spacecraft from the intense temperatures of re-entry. Eventually, the shuttle would land gently on the runway, ready to be prepared for another flight. This made it the first partially reusable space transportation system. Between 1981 and 2011, the Space Shuttle flew 135 missions. During that time, it helped build the International Space Station, launched major scientific satellites, and carried astronauts from many countries into orbit. The shuttle also launched the Hubble Space Telescope, one of the most important observatories ever placed in space. Hubble has transformed our understanding of the universe, capturing images of distant galaxies, nebulae, and cosmic phenomena that were once beyond our reach. In more recent years, another rocket has become famous for a different reason: the Falcon 9, developed by the company SpaceX. Unlike most rockets of the past, Falcon 9 was designed with a clear goal in mind: reusability. Engineers wanted to build a rocket whose first stage could return to Earth and land safely after launch. At first, this idea seemed almost impossible. Landing a rocket vertically after traveling to space required extremely precise control. But after many tests and experiments, SpaceX achieved a historic breakthrough. In 2015, a Falcon 9 booster successfully returned to Earth and landed upright on a landing pad. The sight of a tall rocket stage descending from the sky and touching down gently was unlike anything seen before in spaceflight. Later landings occurred on floating platforms in the ocean. The boosters would fire their engines during descent, slowing themselves before landing vertically. This achievement changed the economics of rocket launches. Instead of discarding the most expensive part of the rocket after each flight, the booster could be refurbished and flown again. Falcon 9 has now completed hundreds of launches, carrying satellites, cargo, and astronauts into orbit. It is used to supply the International Space Station and launch large networks of communication satellites. Its reusable boosters have demonstrated that rockets can operate more like aircraft, returning, landing, and flying again. This approach has dramatically reduced the cost of reaching space. Each of these rockets represents a different chapter in the story of spaceflight. The Saturn V showed that humanity could reach the moon. The Space Shuttle demonstrated that spacecraft could be reused and operate as orbital vehicles. Falcon 9 introduced a new era of reusable rocket boosters and commercial spaceflight. Together, they illustrate how rocket technology continues to evolve, from enormous expendable rockets of the past to increasingly efficient and reusable systems of the present. Yet the story of rockets is far from finished. Engineers and scientists around the world are already designing new vehicles that may travel even farther. Some rockets may carry humans back to the moon. Others may one day journey to Mars. And as technology continues to improve, the dream that once seemed impossible, leaving Earth and exploring the cosmos, moves steadily closer to reality. In the next part of our journey, we will explore one of the most exciting developments in modern spaceflight: rockets that not only reach space, but return safely to Earth, ready to launch again. As we look toward the future, the story of rocket launches is far from finished. In fact, it may only be beginning. For more than half a century, rockets have carried satellites, scientific instruments, and astronauts into orbit around the Earth. They have allowed us to study distant planets, observe the universe through space telescopes, and maintain the delicate network of satellites that supports modern life. But the rockets of the future may take humanity even farther, beyond Earth orbit, beyond the moon, perhaps one day even to other worlds. Engineers around the world are already designing the next generation of launch systems machines, far more powerful, efficient, and reusable than anything that has come before. Among these new vehicles, one rocket in particular has captured global attention: Starship. Starship is being developed as one of the largest rockets ever constructed. When fully assembled with its massive booster stage, the system will stand nearly 120 meters tall, making it even taller than the Saturn V. The rocket consists of two main parts: the Super Heavy booster, which provides the thrust needed to leave the launch pad, and the Starship spacecraft, which sits on top and carries cargo or astronauts into orbit and beyond. Unlike most previous rockets, the entire system is designed to be fully reusable. After launch, the booster is intended to return to Earth and land vertically. The Starship spacecraft itself may also return and land in a similar way. If successful, both parts of the rocket could be reused again and again. This could dramatically reduce the cost of launching missions into space. Starship is designed to carry enormous payloads. It may be capable of lifting more than 100 tons of cargo into orbit. That kind of capacity opens the door to new possibilities. Large space stations could be assembled more easily. Massive scientific observatories could be launched in a single mission, and long-distance spacecraft capable of traveling to other planets could be built and fueled in orbit. But one of the most exciting goals associated with Starship is something even more ambitious: human missions to Mars. Mars has fascinated humanity for centuries. Through telescopes, astronomers have studied its reddish surface and changing seasons. Robotic spacecraft have explored its deserts, mountains, and ancient riverbeds. We now know that Mars once had liquid water flowing across its surface billions of years ago. Today, it remains one of the most promising places in the solar system to search for evidence of past life. But sending humans to Mars is an enormous challenge. The journey requires traveling tens of millions of kilometers through space. Astronauts would spend many months in transit before reaching the planet. To make such missions possible, powerful and reliable rockets are essential. Starship is one of the vehicles that may help make this dream a reality. Beyond chemical rockets like Starship, scientists are also exploring entirely new types of propulsion. One of the most intriguing possibilities is the nuclear thermal rocket. Unlike traditional rockets that burn chemical fuel, nuclear rockets use the energy produced by a nuclear reactor. In a nuclear thermal engine, hydrogen propellant is heated to extremely high temperatures inside a reactor core. The hot gas then expands through a nozzle, producing thrust. Because nuclear reactions release enormous amounts of energy, these engines can be far more efficient than chemical rockets. This means spacecraft could travel faster while carrying less fuel. For long journeys through the solar system, this advantage could be very important. Nuclear propulsion has been studied for decades. In the 1960s and 1970s, engineers in the United States conducted several experiments with prototype nuclear rocket engines. The results were promising. However, the program was eventually cancelled before the technology could be used in space missions. Today, interest in nuclear propulsion is growing once again. Several space agencies are studying how these engines might help send astronauts to Mars more quickly. Shorter travel times would reduce the risks associated with long-duration spaceflight. It could also make future missions safer and more practical. Another idea being explored involves in-orbit refueling. Instead of launching a spacecraft with all its fuel from Earth, smaller tanker rockets could deliver fuel to the spacecraft once it is already in orbit. This would allow spacecraft to begin long journeys with full fuel tanks, without requiring a single enormous rocket at launch. Such techniques may become essential for deep space missions in the future. They could enable large interplanetary spacecraft to assemble and prepare for their journeys while orbiting the Earth. As rocket technology advances, the pace of space exploration may accelerate dramatically. In the early decades of spaceflight, launches were rare and extremely expensive. Today, rockets launch far more frequently. Reusable boosters, new propulsion technologies, and improved engineering methods are steadily lowering the cost of reaching space. Each improvement makes it easier to explore new destinations. The Moon may soon host permanent human research stations. Mars may become the next great frontier for exploration. And beyond Mars lie countless other worlds waiting to be studied. Yet even as rockets grow more powerful, the basic idea remains the same as it was centuries ago. A rocket moves by pushing hot gases downward. The reaction pushes the rocket upward. It is a simple principle, described long ago by Newton's third law. From this simple law, engineers have built machines capable of carrying humanity beyond the surface of the Earth. Machines capable of reaching the Moon. Machines capable of exploring the planets. And perhaps someday, machines capable of carrying people across the vast distances between the stars. For now, rockets continue to rise from launch pads around the world. Each launch represents a moment of transformation. Fire and thunder lifting machines into the sky. Carefully engineered technology overcoming the pull of gravity. And with every launch, humanity takes another small step into the wider universe. In the final moments of our journey tonight, we will reflect quietly on what these remarkable machines have made possible and what adventures may still lie ahead among the stars. For thousands of years, humanity stood beneath the night sky and wondered what lay beyond. The stars shimmered above every civilization that has ever existed. Ancient travelers, poets, and scientists all looked upward and imagined distant worlds floating in the darkness. But for most of human history, those worlds remained forever out of reach. Gravity held us firmly on the surface of the Earth. The stars belonged to the sky alone. Then, slowly, something changed. Human curiosity began to turn into engineering. Ideas turned into machines. And one day, with fire and thunder, the first rockets rose from the ground and carried our technology into space. Rockets became the bridges between Earth and the cosmos. Each launch was more than just a machine leaving the ground. It was a doorway opening, a path connecting our small planet to the vast universe beyond. With rockets, humanity placed satellites around the Earth that help us communicate across continents. We launched telescopes that revealed distant galaxies billions of light years away. We sent robotic explorers to the Moon, Mars, and the outer planets. And for the first time in history, human beings themselves left the Earth and traveled into orbit. All of this began with the simple idea of a rocket pushing fire downward to rise upward. Yet even after all these achievements, the journey has only just begun. The rockets we launch today are only the first steps in a much longer story. Future rockets may carry astronauts back to the Moon. They may take the first human explorers to Mars. One day, they might even travel farther still to the icy moons of Jupiter, the distant worlds of the outer solar system, or destinations we have not yet imagined. Every rocket launch reminds us that exploration is part of what makes us human. We look outward. We ask questions, and we build machines that allow us to go farther than the generations before us. But for tonight, our journey can slow down. The launch pads grow quiet again, the engines fall silent, and the rockets that carried us through this story drift gently into orbit around the Earth. Imagine them there now, circling the planet far above the clouds, gliding through the quiet darkness of space. Below them, the Earth turns slowly beneath the stars. As you relax and prepare for sleep, you might imagine yourself watching a rocket launch from a quiet distance. The engines ignite. A bright column of flame rises into the night. The rocket climbs higher and higher until it becomes only a small point of light moving among the stars. And then, slowly, it disappears into the darkness of space, leaving behind only the quiet sky above. Thank you for joining this peaceful journey through the science of rocket launches. Wherever you are in the world tonight, I hope the story helped your mind drift gently among the stars. Now it's time to rest. Let your breathing slow. Close your eyes and imagine the endless universe waiting quietly beyond the Earth. In a moment, soft ambient music will begin. Let that music guide you into a calm and restful sleep. Good night, and sleep well.